So let's have a look at trigonometric levelling. I think we've got a fair few resources and notes that tell us the ins and outs of trigonometric levelling with regards to curvature and refraction and the various aspects of that. But let's have a practical look at some particular situations. Okay, so first up we're going to look at curvature and refraction applied as a height correction. So the formula that we're going to use for curvature is plus 0.673 times k squared in meters, where k is the distance in kilometers. It is always a positive correction, and it's added algebraically to the vertical component. This is derived from the combined curvature and refraction formula C equals S squared bracket 1 minus 2k slash 2r, which is explained in the notes and resources that you have available. To obtain the true height difference of height between the station and the ground marks, the addition of the height of instrument I and the deduction of the height of target T must be incorporated. The formula then becomes HB minus HA, which is the difference in height, equals S tan of the horizontal angle plus C plus the height of instrument at A minus the height of the target at B. We're going to use as an example an observation from Minden to Mount Minnie. The horizontal angle has been observed at minus 0 degrees, 0 minutes 42 seconds. The instrument height 1.52, height of target 1.58. The RL of Minden, which is the point we're observing from, the HA of Minden, 354.26. And the horizontal distance between Minden and Mount Minnie is 2283.95. So to find the RL of Mount Minnie, the curvature and refraction correction would be equal to 0.673 times 2.284, rounding to the nearest metre and converting to kilometres, and that would give a value of 0.3511. Notice that we've kept that at 4 decimal places just to retain accuracy throughout the calculation. Now S tan 0 degrees 0 minutes 42 seconds equals negative 0.4651 plus the instrument height minus the target height at Mount Minnie is a negative 0.06. So that would be obtained by subtracting 1.58 from 1.52. So 1.52 minus 1.58 gives us 0.06. Notice how we're retaining the signs. And the height of A, or the RL of Minden, 354.26. So we add all those together, 354.26, negative 0.06, negative 0.4651, plus 0.3511, adding them all algebraically and rounding to the nearest centimetre, we get the height of Mount Minnie at 354.09. Now, using the same example, we're going to calculate the difference in height by applying curvature and refraction as a correction to an angle. Previously, we applied it as a correction to a height. So in this instance, we use a different formula. So we have the height at B minus the height at A, which is the difference in height, is equal to S being the distance, tan HA plus C plus the instrument height at A minus the target height at B, where the correction C is in seconds of arc and is derived from the formula C equals S times 1 minus 2K over 2R times the arc in seconds. This gives the correction to an angle. So using the mean value of R for New Zealand, and be careful if you're in other countries, and adopting the coefficient of refraction K as 0.07, the correction then takes the simpler form, it's been simplified, as C equals plus 0.0139 seconds times S, where S is in meters. Remember to treat angles of elevation as positive, so if you're looking up, positive angles, and angles of depression looking down are negative. Okay, now we're going to have a look at some reciprocal observations. This is where we observe the difference in height from each end of the line, and this cancels out curvature and refraction, so we don't have any need to apply a curvature and refraction correction when we do reciprocal observations. The formula that we use, which you'll find within your notes for the difference in height, is S tan a half, each of the angles that we measure, plus 1/2 of the instrument height at A plus the target height at A, minus the instrument height at B plus the target height at B. This is all set out just below here, and S is the horizontal distance between the stations. So just using our previous example, taking reciprocal observations to calculate the true height of Mount Minnie, we look at the observation that we have from Minden to Mount Minnie remains the same. However, our observation, we have now an additional observation at Mount Minnie to Minden, with a vertical angle of minus 0 degrees 0 minutes 12 seconds, height instrument 0.24 meters, height of target at A is 0.32 meters, and of course the horizontal distance between them remains the same. So let's just have a look at the station A, which is Minden, and what we're going to do there is take the instrument height at A plus the target height, add them together, gives us 1.84, which we'll call A. And looking at station B, Mount Minnie, take the instrument height there plus the target height, so that's 0.24 plus 1.58 gives us 1.82, which we will call B. So now working out that part of the formula concerning the instrument heights, we take half of A minus B, which is 0.01. Going to the formula for the angles, we take half of our two angles, which is negative 0 degrees 0 minutes 42 seconds, and from that we subtract negative 0 degrees 0 minutes 12 seconds. So this will give us a algebraic sum of 0 degrees 0 minutes 15 seconds. Then putting that into our formula, S tan H, to give us the sort of difference in height, we multiply that by the distance, 2283.95 tan 0 degrees 0 minutes 15 seconds, and that gives us negative 0.17. Therefore we can put all of that together to work out our difference in height, all the various bits of the formula, and we get negative 0.17 plus 0.01 plus 354.26, which, adding all that together, gives us 354.10. We compare that with the single observations that we did, where we calculated the distance, the difference in height, or the RL, of 354.09 meters. So a little bit different, but not significantly different. The reciprocal observations cancels out the curvature and refraction corrections altogether, so we don't need to have to worry about them, but compares favourably with the single observation in either case, where we either applied the curvature and refraction correction to the difference in height or to the actual angle itself. These sort of calculations lend themselves very well, particularly if we're doing a number of them, to an Excel spreadsheet where we can quite easily calculate out the heights with the information that's available from each end. So there you have it, a bit of a look at trigonometric heighting using the total station or theodolite to measure vertical angles.